In the last video, we met the definition of matrix multiplication. Now we're going to explore some of its properties. Because the definition was quite complicated, let's begin with a recap. First of all, we only define the product of two matrices when the number of columns of the first matrix equals the number of rows of the second matrix. Otherwise, it's simply not allowed. Secondly, there's a rule for the size of a matrix product. If A is m by n and B is n by p, then the number of columns of A is n, the number of rows of B is n, so we're allowed to do the product, and that product A times B will be m by p. You can think of that as the n's in the middle cancelling out. Finally, there are several equivalent ways to specify the entries in a product A times B. First of all, there's a formula in sigma notation. A times B is the matrix whose ij entry is equal to the sum from k equals 1 to n, the number of columns of A, of the ik entry of A times the kj entry of B. Secondly, we can make the observation that matrix multiplication works column-wise. That means to compute A times B, you can find that as the matrix whose first column is A times the first column of B, and whose second column is A times the second column of B, and so on, using the definition of matrix times column that we met in the middle of our previous video. Finally, we can specify the ij entry of a product A times B by using rows times columns. The ij entry of A times B is the ith row of A times the jth column of B, where that multiplication of rows times columns is the thing which looks a bit like a dot product that we met right at the start of our last video. Let's discuss some of the properties of matrix multiplication that make it quite similar in some ways to multiplying ordinary numbers. To state this proposition, we'll take two matrices A and A prime, which are m by n. And here I don't mean that A prime is the derivative of A or something like that. A and A prime are two completely independent matrices which just happen to have the same size. Let's let B and B prime both be n by p, and again there's no relation between B and B prime, they're just two different n by p matrices. And finally, let's let C be p by q and L be a number. Then statement 1 is the associativity property for matrix multiplication. It says that A times, in brackets, B times C is equal to, in brackets, A times B times C. And here you can see why I needed these matrices to have those particular sizes. In order for those products to be defined, I need that this n really is the same as this n, and this p really is the same as this p. So that restriction is just so that part 1 makes sense. Part 2 is a distributivity property. It says that if you add A and A prime and then multiply that into B, that's equal to A times B plus A prime times B. And similarly, A times B plus B prime is equal to A times B plus A times B prime. And finally, a kind of associativity property except with a scalar multiplication as well as a matrix multiplication. This third property says that L times A times B and L times A times B and A times L times B are all equal to one another. I'm not going to prove properties 2 and 3. If you'd like to see proofs of those, you can find them in the online notes for 0007. I will do a proof of property 1, the associativity property, on our next slide. So here it is. As a reminder, A was an m by n matrix and its ij entry was little a subscript ij. B was an n by p matrix and its ij entry was bij. And C was a p by q matrix whose ij entry was cij. So in that case, A times B times C and A times B times C, those are both matrices of the same size, namely m times q. So to show that they're equal, we just need to check that the ij entry in AB times C is equal to the ij entry in A times BC for any I and for any j. So let's fix numbers I and j and work out the ij entry in A times B times C. To begin that, we'd better work out the ij entry of AB. And of course we have a formula for this. This follows directly from the definition. It is the sum from k equals 1 to n of A times aik times bkj. So if we now want to work out A times B times C, well, again, we should use the formula. And this time the formula would say that this is the sum from L equals 1 to P of the IL entry of AB times the LJ entry of C. I'm using L as a different dummy variable to K here just because we're going to end up with two sums, 1 over K and 1 over L, so it would be confusing. In fact, it would be wrong if I used the same variable twice. So I've picked a different dummy variable, L. It doesn't make any difference what it's called. Anyway, there's a bit of extra notation here, which is that this, where I've written AB subscript IL like this, I'm just temporarily using this to refer to the IL entry of A times B. Okay, so now we've written down this formula using the definition of matrix multiplication. We can substitute in our formula for the IL entry for AB. Just substitute J equals L in that formula at the top here. So then what we get is this. And if we multiply the CLJ through that sum and just collect the two sums together, then what we would end up is this, the sum from L equals 1 to P of the sum of K equals 1 to N of AIK times BKL times CLJ. So that is the IJ entry in the matrix product A times B times C. Let's now work out the same entry of A times B times C. So again, the right place to start is by working out the ij entry of B times C. And again, that's just obtainable using the formula. That is the sum from L equals 1 to P of BIL times CLJ. Again, the dummy variable L I choose really doesn't matter, and I just choose it to be L because it will happen to make the formula that comes out look a little bit nicer. Anyway, now we know this, we're able to work out the ij entry of A times BC. It is, again, using the definition of matrix multiplication, the sum from K equals 1 to N of AIK times the KJ entry of B times C. And again, I'm using a bit of special notation here, which I haven't used before, so let's just label it to say what I mean. This thing here, what I mean by this, again, is the KJ entry of B times C. Okay, so let's substitute into this formula here the KJ entry from BC obtained by looking at our formula for that, for the entries of B times C. So if we do this, we get a summation in here, and if we just multiply that AIK through the sum, then what we would have is the sum from K equals 1 to N of the sum from L equals 1 to P of AIK, BKL, CLJ. So let's notice that we actually have the same thing in both of these sums. So this here and this thing here are identical. They're both AIK, BKL, CLJ. The only difference is that the sums occur in a different order. And the first time we got the sum equals from L equals 1 to P, and then the sum from K equals 1 to N. And the second time we've got the K sum and then the L sum, the opposite way round. But that doesn't make any difference. If you do the K and L summations in the opposite order, you get the same terms added up in a different order. But when we add things up, it doesn't matter what order we add them up in, and therefore these summations are equal. We've proved that the two matrices ABC and ABC have the same size and the same ij entry for any ij, therefore they're equal matrices, and this matrix multiplication really is associative. So you ought to have two complaints really about this proof. First of all is, or at least two complaints about matrix multiplication so far. I mean, the first complaint is, why have I defined matrix multiplication in this way? I didn't really give any motivation for the definition that we made for matrix multiplication. The second is, why is this proof so awful? It's a big pile of symbols. There doesn't seem to be any insight as to what's going on there. So it can't really be the right way to do this proof. Well, what we're going to find out later on is an answer to both of these questions, because we're going to learn that matrix multiplication is actually a special type of function composition, and that's why it's defined the way it is, to reflect a particular kind of function composition. But you know that function composition is always associative, so that's where the associativity property comes from. And the reason we have to do such an awful proof is because we don't know exactly how to interpret matrices and matrix multiplication as function composition. So let's look now at a way in which matrix multiplication is not like ordinary multiplication of numbers. And that is that matrix multiplication is not always commutative. So we'll make this definition that two matrices A and B commute if A and B, AB and BA are both defined and they are equal. So they won't always both be defined. Sometimes you can multiply A times B, but you can't multiply B times A. But two matrices commute if AB and BA are both defined and they are equal. Here's an example where both products are defined. We take A and B to be these 2 by 2 matrices. If you then work out A times B, you get this, and if you work out B times A, you get that. And the observation I want you to make is just that AB is not equal to BA in general. So of course there are some matrices which do commute, but in general matrix multiplication is not necessarily commutative. In fact, if you pick any two 2 by 2 matrices at random, then it's very likely that they won't commute. When you multiply numbers, there is a special role for the number 1, in that if you multiply something by 1, you don't change it. A similar role for matrix multiplication is played by the identity matrix, which I'm going to define on this slide. The n by n identity matrix, which we write as I subscript n, is the matrix whose ij entry is 1 if I equals j and 0 otherwise. So here is I2, its 1 1 entry and its 2 2 entry are 1, and its 1 2 and 2 1 entries are 0. And here is the 3 by 3 identity matrix I3. You can see the 1 1, 2 2 and 3 3 entries are 1, and all the other entries are 0. That's the definition of the identity matrix. So I said that the identity matrix behaved like 1 under multiplication. Here is a lemma that states that. It says if A is an m by n matrix, well, let's just think a bit carefully about these products. M is m by m, A is m by n. So the product Im times A makes sense, and it will be m by n, because the two m's in the middle cancel out. And in fact, Im times A is equal to the m by n matrix A. And similarly, A times In, again this makes sense, and again it's equal to A. We're going to do a proof of one of these. In fact, we'll prove the first equality, that Im times A is equal to A again. So let's do that, using the definition of matrix multiplication. So as some notation, we'll let A be the matrix whose ij entry is lowercase a subscript ij. And we'll also have some notation for the ij entry of the m by m identity matrix. We'll call it delta ij. And what that means from the definition of the identity matrix is that delta ij is 1 if I is equal to j, and 0 if I is not equal to j. Now we know that Im times A and A have the same size. So all we have to do to check that they're equal is to check that they have the same ij entry for any I and for any j. So we can use the formula for a matrix product to work out the ij entry of Im times A, and we should show that this is equal to little lowercase a ij, since that's the ij entry of A. So let's use that formula. The definition of our matrix multiplication is that Im A is the m by n matrix whose ij entry is the sum from k equals 1 to m of delta ik times akj. But this term is going to simplify a lot, because all but one of the terms are guaranteed to be 0. If k is not equal to I, then delta ik is 0, so it contributes nothing to this sum. So we only need to think about the term when k is equal to I, because that's the only one which could possibly be non-zero. Every other term will contribute 0 to this sum. So only the k equals I term contributes, and what that gives us is delta II times Aij. But delta II is 1, so we've got 1 times Aij, which is just Aij. So the ij entry of Im times A is Aij, and that means our two matrices Im times A and A have the same size and the same ij entry for any I and for any j. Therefore, they're equal. If you want to see a proof of the other equality, you can have a go yourself, or you can find it in my online notes for 0007.